Okay, here we need to find the exact perimeter of the trapezoid. This is just doing some work with the 30, 60, 90 and 45, 45, 90 triangle relationships. So we can see that these two angles give us a hint that that's what we're going to do. So what I'm going to do first here is I'm just going to draw the height of this trapezoid in, and that's going to create some triangles for me. The first thing to note is that the segment here is going to come down as 3, so that'll give us a piece of the perimeter. And now we just need to find the rest of these sides of these triangles to complete the work here. So the 45, 45, 90 triangle on the right, we have no information other than the angle, so we can't do anything with that one yet. But we can work on the 30, 60, 90. So here, this is the 30-degree angle. And again, it's just remembering the hopefully are now be feeling like straightforward relationships. So the side across from the 30-degree angle is always half the hypotenuse. So this is going to be 15 divided by 2. And then the height, which is the angle across from 60 degrees, is always going to be this side here times square root of 3. 15 over 2 times root 3 is the side here. Again, it's just remember the relationships here. If this is a 60 and this is a 30, the relationship is 1, square root of 3, 2. So all I'm doing is applying that idea here. And now that we have the height from the triangle on this side, we know that that's the height or the side of the triangle over here, 15 root 2 over 3. And so these sides are congruent in a 45, 45, 90. So this segment down here is also 15 halves root 3. And then in a 45, 45, 90 triangle, we know that the pattern's 1, 1, square root of 2. So if we have a leg, we can multiply by square root of 2 to get the hypotenuse, and that's what we're going to do here. 15 halves square root of 3 times square root of 2 gives us that leg here. So now we have all of our pieces, and so it's just going to be a little bit of work to add them all up. So we're going to have the top piece of 3. We have this side of the triangle, 15 halves times root 3 times root 2. That's going to be actually root 6. So 15 root 6 is that piece. Down here we have 15, I should have said 15 halves root 6. Sorry about that. Here we have 15 halves root 3. We have this 3 here, plus 15 halves, plus this 15 here. And so now the question is, can we add all these pieces up here together? We can add it to the 3, this 3, this 15 halves, and this 15. So 15 plus 3 is 18, plus another 3 is 21, plus 15 halves. So those add up to 28.5. The 15 halves root 3 doesn't combine with anything else because root 6 and root 3 can't be combined. So we'll keep that as 15 halves root 3, and then 15 halves root 6. Which it looks like the answer key has these as decimals, so you can just rewrite this as 28.5 plus 7.5. That's the same as 15 halves root 3 plus 7.5 root 6. Kind of a lot of messy numbers here, but hopefully a relatively straightforward idea of what to accomplish here. But the radicals involved here make it a little bit messy to work with. Okay, number 52. This is just going into right triangle trigonometry, and this is a relatively basic idea here. So the key thing to do with right triangle relationships is to remember the relationship that sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And you can remember this with that mnemonic so, ka, toa, which is how most people remember how these go together. But I wrote it here with the ratios so you can see exactly what's going on here. So this is just says to find the sine, cosine, and tangent for angle B here. So the sine of angle B is going to equal opposite over hypotenuse. So the side opposite angle B is 15, and the hypotenuse of this right triangle is 17. Cosine of B is going to be adjacent over hypotenuse. The adjacent side to angle B here is 8, the adjacent leg I should say, because the hypotenuse is also adjacent, but it's not a leg. So the cosine is 8 over 17, and tangent of angle B is going to be opposite over adjacent. Opposite is 15, adjacent is 8, so that answer will be 15 over 8. So here we're asked to find the tangent of 30 degrees without just punching it in the calculator. And so the hint is an important piece here. It says use special right triangles, and by that we mean 30, 60, 90, or 45, 45, 90. Since we're trying to find the tangent of 30 degrees, this one's not going to be useful to us. So let's just go ahead and draw a special right triangle with a 30-degree angle. So this is 30, we know this is 60. And the pattern, again, I like to remember, is that the shortest leg, I call it 1. The hypotenuse is always double the shortest leg. And then the longer leg is the shorter leg times square root of 3. So 1 times square root of 3. Now, if we want the tangent of 30, we can use this special right triangle. Tangent of 30 is going to equal, remember, so, ka, toa, opposite over adjacent. So if we look at this angle here, which is 30, opposite is 1, adjacent leg is root 3, and that would be okay to leave it that way, or if the answer key has the radical eliminated from the denominator, so I'm going to multiply it by the funny form of 1, which is root 3 over root 3. So that's going to be 1 times root 3 is root 3, root 3 times root 3 times root 3 is 3, and so that's the answer in the answer key. But this would be an acceptable form as well. This problem is asking for tangent ratios. Tan is the TOA part, so tan of an angle is going to be opposite over adjacent. So we're asked to find the tangent ratios for each of these two angles. So for angle P, tangent of P, that opposite is 20, that adjacent is 21, so that's 20, 21, and then tangent of Q, the opposite angle from Q, the opposite side from Q is 21, the adjacent is 20, and so that answer would be B. Notice how those are reciprocals of one another. That is not a coincidence. So as you can see, like this, you can see the same two legs are involved. In one case, it's one over the other in each case. So you don't need to remember that. I just thought I'd point it out in case you found it interesting. Okay, here we're encountering the reason why trigonometry was essentially invented. When we know an angle and one side of a right triangle, we can use trigonometry to find the measures of the other sides. And so the way to approach this problem is we know trig ratios involve an angle, so we want to center in on an angle where we have the measure. And so here we have a 55 degrees, and then take a look at what we're trying to find and what we need. Here we can see that we're trying to find the adjacent angle, and we have the opposite angle. So since the hypotenuse is over here, but it's not really part of the problem. So as we think about SOHCAHTOA, TOA is going to be the one that's going to be helpful to us here because that's the information that's involved. So I'm going to use a tangent ratio. So tangent of 55 degrees is going to be opposite over adjacent. The opposite is 8.9, adjacent is unknown and x. And so we have tan of 55 degrees equals 8.9 over x. I'm going to multiply both sides by x here to get rid of the denominator. So we have x tan 55 equals 8.9, and then we have to get x by itself, so now I'm going to divide by tangent of 55 degrees, which is just a number. Don't get thrown off by the fact that it says tangent 55. It's a number, we just don't know what it is. Those are going to cancel, and then x is 8.9 divided by tan 55, and if you punch that into your calculator, you get approximately 6.2 centimeters. There's a couple things we can do to reasonableness check this. We know that the other angle in this triangle is 35. And so x here should be the smallest side because the smallest side is always opposite the smallest angle. And look, so 8.9 is actually greater than 6.9, so it seems to pass muster on that measure. One other thing I want to make sure is make sure that your calculator is in degree mode when you're doing these problems. You look up in the upper right corner and it says, degree, you're in good shape. But if it says RAD, radian, you want to make sure to change it into degree mode. If you're not sure how to do that, send me an email, because radians, as you think you know, are a different way of measuring angles. And so that's what you have to do there. Here in this case, we are trying to find an unknown angle, but I'm going to use the same kind of idea here, that I'm going to focus in on the either angle that I have or the angle that I'm trying to find, and then think about the trig ratios from the vantage point of that angle. So that's the angle we're looking for. What do we have? Well, we have the opposite side, and then we have the hypotenuse. And so when we think about SOHCAHTOA, we have an opposite and a hypotenuse. Looks like sine is what we're going to want to use. So we're not going to use cosine, we're not going to use tangent. Sine of this unknown angle, x degrees, is going to be opposite over hypotenuse, which is 7/15. And this is where you have to do the inverse trig ratios to solve for this equation. So on your calculator, what you're going to do is x degrees is equal to the inverse sine of 7/15. So I'm just taking that 7/15, and that's going to tell me the angle of x degrees. I'm kind of undoing the sine function here. So if you go ahead and put that in your calculator, again, making sure you're in degree mode, you'll get x equals approximately 27.4 degrees. Actually, I was just checking on my calculator. The answer key shows 27.4 degrees. When I do this on my calculator, I show it as 27.818 degrees. So I feel like that's a more accurate answer. I didn't check every single answer here, so it looks like that just could be a typo, 27.4. But hopefully you used this process here. Okay, so we're just going to use that same process I outlined in the last couple of problems. 70 degrees is the angle we have. We're looking for the adjacent portion to that angle. We have the hypotenuse, and so we have A and H, and that's going to give us the Ka ratio. So cosine is what we want to use here. Cosine of 70 degrees is going to equal adjacent over hypotenuse, which will give us x, the unknown x of adjacent, over 80, which is the hypotenuse. And so cosine 70 degrees equals x over 80. To solve this, I'm going to multiply both sides by 80 to clear the fractions here. So the 80s cancel. 80 divided by 80 is 1. X is going to be 80 times cosine of 70 degrees. So x equals 27.4. Now I see what I did wrong in that last problem. So this is x equals approximately. I was reading the wrong thing on the answer key. If I scroll back to number 56 here, this actually, see, 56 is answer C, so 28. So yeah, so forget this here. That was just, I read the wrong answer. So 27.8 is what you get, and that rounds up to 28 degrees, which is why you get answer C on 56. Sorry about that. '58. Trying to find J and K here. So here we have two unknowns. So there's lots of different ways you can approach this problem. Maybe the first one is since we're looking for K, this is a right triangle. We have two sides here. We can just use Pythagorean theorem. Like leg 1 squared is 14 squared plus leg 2 squared is K squared is going to equal 50 squared. So K squared equals 50 squared minus 14 squared. And if you put that in your calculator, K squared is 2304. So K is plus or minus the square root of 2304, which equals plus or minus 48. And again, we cancel. I've said this in a prior video. You throw away that negative solution because it's not helpful. So we know K equals 48 here. And now we need to find angle J. Here we have all the measures of the triangle, or all the sides of the triangle, so you can just pick your favorite ratio. I'm going to go ahead and pick sine, just because. So opposite is 48, so that's our opposite. This is our hypotenuse, and that's our adjacent. So you can pick your favorite trig ratio. I'm just going to use sine. So sine of j degrees equals opposite, which is 48, over hypotenuse, which is 50. And so j is going to be the inverse sine of 48 over 50 in order to solve that equation, which gets me 73.7 degrees. So that's our two pieces of information here. K equals 48 and J equals 73.7 degrees. I think you'll find this to be a straightforward word problem, number 59. It's just really trying to visualize what's going on here. So we have a 17-foot ladder leaning against a wall. So walls go up and down. So I'm going to draw the wall here. And the 17-foot ladder leans against the wall. So ladders lean against walls this way. So that's the ladder. We know it's 17 feet. Walls are typically perpendicular to the ground, so that's a right angle. And we're trying to find... Oh, and it says that it's telling us that this is 15. So the height above the ground where it's leaning is 15. We're trying to find the distance from the foot of the ladder, which is right here, to the wall. This looks like a right triangle. We have a hypotenuse in one leg. If I call this distance d, we're just using Pythagorean theorem to solve this. So d squared is one leg squared plus 15 squared equals 17 squared. D squared equals 17 squared minus 15 squared, just subtracting that from both sides. D squared will equal 64. So D equals plus or minus the square root of 64, which equals plus or minus 8. Throw away the negative. D is going to be 8. You could have also recognized this as a Pythagorean triple, because 8, 15, 17 is a Pythagorean triple. So we could have gone right to the answer that way as well. Okay, here's an angle of elevation problem. We have Snoopy flying a kite on a 60-foot string. He's holding the string at a height about 3 feet above the ground. So let's go ahead and draw the ground here. I'm going to pick a spot 3 feet above the ground. That's where the string is being held. String makes a 70-degree angle of elevation with the horizontal. So that's our horizontal there. Angle of elevation is going to be up here. That's 70. So that's what 70, that's angle of elevation is always measured from a horizontal, so something parallel to the ground. How high above the ground is the kite? So we know that the kite is 60 feet here, so we have to find a triangle here to figure out what's going on. Or let's see, actually we're going to have to use trig here. So we don't have two sides, we only have one side of the triangle, but we do have an angle. And so height above this h right here is what we want to find. If we use this as a reference angle, we can tell that h is the opposite. We know that 60 is the hypotenuse. So SOH, we're going to use sine, because SOH. Sine of 70 degrees equals h over 60. H equals 60 times sine of 70 degrees. If you plug that in your calculator, you get 56.38, which rounds to 56.4 feet. But don't forget, the string here is 3 feet above the ground, so we need to add this 3 here to get the final answer above the ground. So we're going to add 3 here to get 59 plus 4 feet. And that's the answer to how high above the ground the kite is.